Okay, well, we continue on with our exercises for section 1, and we'll just have a look at the questions 17 through to 20. So 17 is just evaluating some of these Legendre symbols using the various tools that we now have. We notice that you're given that this number down here is prime and 2137 is also prime. So here is the solution of this one. So we're starting off with 666 over 2137, and of course the main technique of this is to factorise the top, and we can see that this is we can factorise this as 6 times 111, and 6 is 3 times 37. So 111 is 3 times 37, so I can write this as 3 squared over 2137 times the Legendre symbol 2 over that times the Legendre symbol 37 over that. Now this is 1, of course, because 3 squared is a square. This has a 2 on the top, so we can use our formula of 2 over p is minus 1 to the p squared minus 1 over 8. And 37 is a 1 mod 4 prime, so I can flip upside down without any problems. When you simplify this, this turns out to be an even number up here, so this is 1. And I read 2137 mod 37, and it's just 28. So again, we can take the square factor out of 28, which is 4, and get rid of that. And we're left with 7 on 37. 37 is a 1 mod 4 prime, so we can flip it using the quadratic reciprocity law. And then again we reduce this down to 2 over 7. Once we get a 2 on the top, we can use our formula, and it turns out to be 1. So this Legendre symbol is 1, which of course means that 666 is a square modulo 2137. And similarly, one can do a similar analysis on this one here, and it turns out to have a Legendre symbol of -1, which means that this number is not a square modulo 19,991. Question 18 gives a little application of this, so we're going to evaluate -31 and 127, and hence prove that this Diaphantine equation has no integer solutions. So it's a nice little application of the quadratic reciprocity result and the Legendre symbol. So for question 18, I won't go through the calculation of this. It's not hard to, you just do the similar thing we did before. These are both primes. You can invert and you can show that this is equal to -1. That's an easy task. So for the Diaphantine equation, we suppose that there are integers x and y that satisfy this equation. So if I put on my mod 127 glasses and read this modulo 127, then I get y squared is -31 on 127. And that would then imply that this is a square modulo 1 on 27. And that means the Legendre symbol -31 over 127 is 1, and that contradicts what we stated up here. So a nice little application of this. Question 19 is a little bit more involved, and it's got various parts to it. We want to prove the following, and I'm just going to do a couple of these to just give you the flavour of it. So we're going to prove that -2 is a quadratic residue if and only if p is 1 or 3 mod 2. 3 is a quadratic residue if and only if p is plus or minus 1 mod 12. And I won't do C and D, leave you to finish those if you're interested in that. So for question 19, for the part A, we want to show that this thing is equal to 1. So I want to know when is -2, for what primes is -2 a square, so that means we want this Legendre symbol to be 1. So I can split this up into two different pieces here, and that will then lead me to 2 cases. So either both of these numbers are 1 to multiply to give 1, or both of these are minus 1. So minus 1 is a square mod p if and only if p is 1 mod 4. So this is 1 if p is 1 mod 4. This is 1 if p is plus or minus 1 mod 8, which we did in the lecture notes. So that's one possibility. Or both of these could be minus 1, in which case this is minus 1 if p is minus 1 mod 4, and this is minus 1 if p is plus or minus 3 mod 8. Now putting these two together, a prime which is 1 mod 4 and plus or minus 1 mod 8, well, you can't have a prime that's 1 mod 4 and minus 1 mod 8, because if it's minus 1 mod 8 then it's 3 mod 4, so it's got to be 1 mod 4 and 1 mod 8, that just means 1 mod 8. And similarly here, if you make a list of what these things look like, minus 1, if p is minus 1 mod 4, then that means it's 3 plus some multiple of 4, and it's also got to be plus or minus 3 mod 8, because it can't be minus 3 mod 8, because then it would be 1 mod 4, so that gives you p as 3 mod 8. So these are the two possibilities here. In the case where 3 over p is 1, if we want to know what primes is 3, and this is all if and only if, by the way, and so we get both parts, both directions. If 3 is a square modulo p, then again I've got to look at two cases. Firstly, I want to be able to turn this upside down, and so 3 is a 3 mod 4 prime, and we need to then worry about whether p is a 1 or a 3 mod 4 prime. So if p is a 1 mod 4 prime, then we can just flip the symbols upside down using quadratic reciprocity, and then we can simply apply Euler, because 3 minus 1 over 2 is 1, and that just immediately, that's true if and only if p is 1 mod 3. So that means p is 1 mod 3 and p is 1 mod 4. These are relatively prime. Chinese remainder says p has to be 1 modulo 12, and that's unique. The other case is if p is 3 mod 4, then both of these are 3 mod 4 primes, and so when you flip it, you get a minus 1 is the penalty. And again, that's true if and only if p is, by Euler, is minus 1 mod 3, because 3 minus 1 over 2 is 1. And now I've got 3 mod 4, which is minus 1 mod 4, and minus 1 mod 3. Chinese remainder again gives you minus 1 mod 12. So that means 3 is a square modulo p if and only if p is plus or minus 1 mod 12, that is, it's 12n plus or minus 1. And questions C and D are done similarly. Finally, question for this section, question 20, show that minus 3 is a quadratic residue, that if minus 3 is a quadratic residue modulo of prime p, then the prime has to be 1 mod 6. So, same idea again. We've got if minus 3 is a square mod p, then the Legendre symbol is 1. And again, we have to look at the various cases of whether p is a 1 or 3 mod 4 prime. If it's a 1 mod 4 prime, then you can take the minus 1 over p out, and minus 1 is a square modulo p, and then you can flip these around without penalty, and so we get p over 3 is 1, and again Euler gives you p is 1 mod 3, so if it's 1 mod 3 and 1 mod 4, it's 1 mod 12. Case 2, if p is a 3 mod 4 prime, then minus 1 is not a square, so the minus 1 over p is minus 1, and when we flip this, so this thing here is minus 1, when I split this, that becomes minus 1, and I get another minus when I flip these around by quadratic reciprocity. I get another minus appearing, so I just again get p over 3 is 1. Euler gives me p is 1 mod 3. Now 1 mod 3 is the same, so the easiest thing here to do is to write out what these look like. So p can be 3 or 7, and here p is 1 or 4 or 7, and the only ones that are common are 7 that satisfy both of these. So you can write these out modulo 12. So it's 3, 7, or 1, 4, and 7, and the only ones that match are the 7 mod 12s. So that tells me then that minus 3 is 1 if and only if p is 1 mod 12 or 7 mod 12. And a shorter way of writing that is to say, well, it's 1 mod 6. So it's just a clever way of writing both of these in one statement. And that's the end of the problems for that little section.